So in 2012, the Waldo Canyon wildfire burned over 300 homes to the ground.
Right. Yeah. It was devastating.
Yeah, but here's the terrifying detail that I found buried in the post-disaster analysis. Most of those homes, they were never actually touched by a wall of flames.
Which just sounds wrong, right?
Exactly. I mean, the trees surrounding them were sometimes left completely unburned. Those homes did not catch fire from the outside. They basically, they inhaled the fire from the inside out.
And that specific detail, it really kind of shatters the comforting illusion we all sort of buy into.
The illusion of permanence.
Yeah, exactly. I mean, we walk past a brick wall or a concrete pillar or, a steel skyscraper, and we subconsciously label it as permanent. We just expect the ground to stay still, the roof to stay overhead, and the exterior to protect the interior.
Right, but when nature actually unleashes its full force, that illusion of permanence just drops away completely. The structures we think are, invincible are suddenly fighting for their lives.
Fighting's a good word for it.
And what we are exploring today with you, our listener, is that the difference between a tragedy and a survival story is, well, it's rarely just luck. It is engineering.
It comes down to structural choices made years or even sometimes decades before a disaster ever occurs.
Exactly. And that is our mission for this deep dive. We've got a really robust stack of sources today. We're looking at guidelines from FEMA, standards from the American Society of Civil Engineers, research from NIST, and some recent engineering reports, too.
It's a lot of material.
It is, yeah. And we are going to explore the global standards, the building codes, and the specific structural strategies that make disaster-resistant construction possible. Basically, we are looking at how to build a world that actually stands its ground.
And to understand how a building survives, you really have to start with the invisible shield that protects us every single day.
Which is the building codes, right?
Yes, modern building codes. Specifically, the International Building Code, or IBC, and a standard known as SEE 7.
Right. So I saw ASCE referenced constantly in our sources. And I mean, it sounds like a really dry technical document, but it seems to dictate literally everything about how we build.
Oh, it does. It is the bedrock of all structural resilience. ASCE 7 dictates the minimum design loads for structures.
Okay.
Think of it as the mathematical DNA for how a building is required to resist forces. It tells an engineer exactly how much wind, how much seismic energy, snow accumulation, and flood pressure a specific building in a specific zip code must be able to withstand without collapsing.
So it's a calculated formula for survival, basically.
Exactly.
And you see the devastating results when that mathematical DNA is just missing or ignored. I mean, we have a recent Reuters report from June 2026 covering a deadly earthquake in Venezuela.
Right, yeah. That was a tragic situation.
It really was. Engineers there were begging for audits of state housing because the damage exposed severe concerns about weak code enforcement and rushed construction as well. I mean, the building might look sturdy on a sunny day, but without that mathematical rigor, the concrete just shatters.
Well, because a building's ability to survive an earthquake relies on this concept called ductility.
Ductility, okay.
Right, which is the ability of a structure to bend, to flex, and to deform without actually breaking.
Oh, I see.
So concrete is extraordinarily strong under compression, meaning it can hold up a lot of weight. But it is remarkably brittle if you do not engineer it with embedded steel reinforcement so it can flex.
A seismic wave will just snap it.
Exactly, it just snaps.
Which brings up a perfect contrast in our sources. We have a report on Levi Stadium in San Francisco, which is built right in the middle of earthquake country.
Yes, a very seismically active area.
And it uses something called buckling restrained braces. Now, when I was reading about the mechanics of these braces, I immediately pictured the shock absorbers on a mountain bike.
The mountain bike analogy is spot on. I really like that. If you ride a bike with a rigid, solid metal frame off a steep jump, the frame takes the full kinetic force of the impact. Right.
And if you do that enough times, the metal just fractures.
But with a shock absorber, you have a mechanism that's actually designed to compress. Instead of a rigid wall stubbornly trying to resist the earthquake and snapping, these buckling restrained braces stretch and compress.
Yes.
They safely absorb and dissipate the kinetic energy of the earthquake.
The stadium is actively eating the earthquake's energy. And what's fascinating here is that this level of seismic safety is not just reserved for, billion-dollar new stadiums.
Oh, really?
No, the engineering principles have to be applied to the everyday buildings we already live and work in. San Francisco, for example, has been pushing to screen nearly 4,000 older concrete buildings.
Well, 4,000?
Yeah, and beyond that, there is an urgent push for soft story retrofits.
Okay, I have seen that term, soft story, around California.
Mhm.
That refers to apartment buildings where the ground floor is mostly open space. Right, like a carport or a garage with living spaces stacked above it. Yes, exactly. So you have, say, 3 stories of heavy apartments resting on a ground floor that is essentially empty air and just a few narrow support pillars.
That sounds precarious.
It is, because ground shaking during an earthquake is primarily lateral. It moves side to side.
Okay.
Those narrow ground floor supports face immense shear forces. They're being pushed horizontally while carrying all that vertical weight at the same time.
And because they lack ductility, like we talked about, they snap, and the building collapses straight down on itself.
Exact.
So a soft story retrofit usually involves, what, installing a steel moment frame around those garage openings? Just to give the building the lateral stiffness it needs to resist that shear force?
Right, because ground shaking tests a building skeleton from below by moving the foundation. But wind attacks the entire envelope simultaneously.
Oh, that's a good point.
The forces at play in a tornado or a hurricane, they require an entirely different engineering philosophy.
I am picturing a house like a Lego set. If I just snap the roof onto the walls, it feels heavy and secure under normal conditions.
Sure.
But extreme wind does not just push the Legos over. It actively tries to reach inside and pull them apart.
Yes, and the National Windstorm Impact Reduction Program studies exactly this aerodynamic interaction. Wind engineering is super complex because a solid brick wall alone does not keep you safe.
Right.
The structure's survival depends entirely on having a continuous load path.
Okay, let's break down how that continuous load path actually functions for the listener.
Okay, imagine holding a kite in a strong breeze.
Okay.
The wind pulls the kite, the string pulls your hand, your arm pulls your shoulder, and your feet hold fast to the ground.
Oh, I get it.
That is a continuous load path. In a house, the roof must be physically strapped to the walls using metal hurricane ties. The walls must be physically bolted to the foundation, and the foundation must be anchored deep in the earth.
So if any one of those connections is missing, the wind will just find the weak link and sever the path.
Exactly, and just having a brick exterior does not guarantee those mechanical connections actually exist inside the framing.
Right, it's just the shell.
It is. And worse, if the envelope of the house fails, you face the danger of internal pressurization.
Internal pressurization.
Yeah, during a hurricane or tornado, if a window blows in or a door gives way, extreme wind rushes inside the house. And because it has nowhere to exit, the house suddenly acts like a parachute.
The pressure inside spikes dramatically, pushing up on the ceiling, while the wind rushing over the top of the roof creates an aerodynamic suction pulling up.
Right. That combined force will literally rip the roof clean off the walls.
Wow.
Once the roof is gone, the walls lose their structural brace and they just collapse outward. The house tears itself apart from the inside out.
And that parachute effect explains why FEMA has strict standards for safe rooms. Specifically, the FEMA P361 and P320 guidelines that we saw in the sources.
Yes.
Because a certified safe room is not just an interior closet, it is an explicitly engineered vault with its own independent, continuous load path.
Exactly. It's totally independent.
It is designed to withstand 250-mile-per-hour winds. And crucially, it is tested to stop extreme wind-borne debris.
The debris testing protocols are rigorous, to say the least. In a tornado, a piece of 2x4 timber flying through the air becomes a lethal projectile.
Right.
A FEMA-certified safe room door has to be able to stop a 15-pound wooden plank shot at it from an air cannon at 100 miles per hour.
Wait, an air cannon?
Yeah, they literally shoot it out of a cannon.
That's wild. And a standard brick wall or, a normal interior bathroom door will simply shatter under those impact forces.
It would just go right through.
So wind uses pressure to tear a structure apart mechanically, but a wildfire uses that exact same wind to bypass the exterior defenses completely.
Yes, exactly.
Which brings us back. Here's where it gets really interesting. Let's return to that Waldo Canyon statistic from the start of our deep dive. You mentioned earlier that homes often burn from the inside out during a wildfire. How does building science actually counter an invisible storm of embers?
Well, the NIST research on the wildland-urban interface, or the WUI, prompted a profound shift in how we think about fire. A wildfire can send a blizzard of burning embers miles ahead of the actual fire front.
Miles ahead.
Yeah. And these embers land on combustible debris on a roof, or they get sucked straight into the traditional attic fence of a house.
Because the attic is full of dry wood and insulation. An ember gets in, starts a smoldering fire, and the home is destroyed before the main fire ever even reaches the neighborhood.
Right.
The sources outline specific home hardening strategies to stop this, starting with a 5-foot non-combustible zone entirely around the perimeter of the foundation.
Which means no bark mulch, no wooden welcome mats, no combustible plants touching the siding. It's about starving the embers of any fuel the absolute moment they land near the house.
And you combine that with ember-resistant vents. Our sources mention they use fine metal mesh and specialized baffles to block embers. But I was wondering, how do baffles actually stop a glowing ember being pushed by a 60-mile-per-hour wind?
That's a great question. So the mesh catches the really large embers, but the baffles act like a miniature maze inside the vent.
Oh, okay.
Embers are carried entirely by the wind. They don't have their own propulsion, obviously. And because they lack momentum, they cannot navigate sharp turns.
Oh, I see.
Yeah, they hit the back of a wall, lose their aerodynamic lift, and safely drop out of the airflow before they ever reach the dry wood in your attic.
It is using the physics of airflow against the ember. That is brilliant. And you pair that with Class A fire-resistant roofing. Just for clarity, what constitutes a Class A rating? Are we talking strictly about metal sheets?
Metal is one option, sure, but asphalt shingles or clay tiles can also achieve a Class A rating. To earn that designation, the roofing material is tested in a lab to ensure it can withstand severe fire exposure without igniting,
Okay.
and without allowing the fire to penetrate the roof deck, and crucially, without generating new flying embers that could threaten neighboring homes.
Right. But I have a practical question for the listener who might be thinking about their own home right now. Aren't these specialized fire-resistant materials, the baffles, the Class A roofs, aren't they prohibitively expensive? It sounds like building a fortress.
You know, that is the common assumption, but the data proves otherwise. Our sources include a study by Headwaters Economics analyzing the construction costs of a wildfire-resistant home compared to a traditional home. And they found the costs are virtually identical.
Wait, really? There is no premium for building a fire-resistant home?
Not really, no. It is primarily about smart design choices rather than luxury materials.
Huh.
Swapping combustible bark mulch for decorative rock in that 5-foot zone does not cost more. Choosing fiber cement siding instead of cedar planks is cost competitive. Installing ember-resistant vents during initial construction adds just a negligible amount to the overall budget.
So the vulnerability comes from a knowledge gap, not a financial barrier. Now, with fire, the entire engineering philosophy revolves around repelling the hazard, right? Starving it before it reaches the walls. But you cannot starve a flood. The water is coming regardless. So how does the engineering philosophy change when you actually have to absorb the threat?
If we connect this to the bigger picture, we are seeing a major philosophical shift at agencies like FEMA regarding water. For a long time, flood control just meant pouring more concrete.
Right, building higher seawalls or deeper concrete channels.
Exactly. But now, the focus is shifting heavily toward nature-based solutions.
Which means restoring wetlands, rebuilding coastal dunes, utilizing oyster reefs.
Because natural systems are highly efficient at absorbing energy. A healthy coastal wetland acts like a giant sponge. It reduces wave energy and lowers the flood depth before that water ever even touches human infrastructure.
So you use nature to do the heavy lifting so the buildings behind it just do not have to fight as hard.
Right, but the buildings still have to fight. And the ASCE 24 standards provide the blueprint for flood-resistant design.
And what really caught my eye in the FEMA guidelines was the stark difference between dry floodproofing and wet floodproofing.
Oh yeah, they represent two totally different philosophies.
Yeah.
Dry floodproofing is what it sounds like. It's sealing a commercial or public building so water simply cannot enter. Use watertight doors, seal the brickwork, and install backflow valves on the plumbing.
You essentially turn the building into a submarine.
You do, yeah.
But you cannot apply that submarine logic to a typical residential house, can you?
Definitely not. If you perfectly seal a regular wood-framed home and a flood surrounds it with 3 feet of water, you face severe hydrostatic pressure.
Because water is heavy.
Very heavy.
Hmm.
It's about 62.4 pounds per cubic foot. The water pushing inward on those sealed walls will literally crush the foundation.
Oh, wow.
Alternatively, because of buoyancy, the trapped air inside the sealed house can pop the entire structure out of the ground like a cork.
Like a cork. Which brings us to wet floodproofing, which is outlined in FEMA Technical Bulletin 7. Instead of fighting the heavy water, you intentionally invite the disaster into your lower living space.
Yes. You design the uninhabited lower areas like a crawl space or an unfinished garage with specific flood vents. When the floodwater rises outside, the vents open and just let the water flow inside.
So by letting the water inside, you equalize the hydrostatic pressure on both sides of the foundation wall.
Exactly.
And it saves the structure of the house from collapsing under the weight of the flood. You design that lower space with materials that can get wet, so when the water recedes, you simply hose it out.
Yeah, it's the ultimate expression of resilience, really. You bend so you do not break.
And there is another strategy for elevated coastal homes detailed in FEMA Technical Bulletin 9 breakaway walls. When you elevate a home on pilings at the beach, you often enclose the space underneath to park a car, right?
Yeah, that's very common.
But during a hurricane storm surge, the force of those crashing waves is devastating. So engineers design those lower enclosure walls to intentionally fail.
In structural engineering, we literally call that intentional failure.
I picture it like a lizard dropping its tail to escape a predator. The wave hits, the breakaway wall completely washes away, and by breaking away, it prevents the wave energy from transferring into the main pilings.
That's it. Just like the lizard, the house relies on the fact that those breakaway walls are entirely non-structural. They do not hold up the building.
Because if they were load-bearing,
The whole house would come down with the wave.
wow.
The house sacrifices the lower walls to save the main elevated structure.
Sacrificing a wall to save a house is brilliant for a residential property. But you cannot apply that logic to a hospital or a school. A community cannot survive, let alone recover, if its core lifelines fail.
Protecting critical facilities requires an entirely different scale of engineering. The sources actually highlight Italy's proactive seismic retrofitting program for schools. They recognized that protecting children and maintaining educational infrastructure is a paramount public priority. And in the U.S., FEMA provides guides like P424 and P1000 dedicated strictly to protecting educational facilities from natural hazards.
But upgrading these lifelines is logistically brutal. I mean, you cannot just shut down a major hospital or a school for 2 years to rebuild it from scratch.
Which is where the concept of incremental seismic rehabilitation comes in. This is a strategy where administrators upgrade structural safety in carefully planned phases over time, rather than all at once.
Okay, so you might fix the roof connections to establish a continuous load path one summer. Then, the next summer, you tackle bracing the unreinforced masonry,
Right.
which, just to clarify for the listener, refers to older brick walls that lack internal steel rebar to hold them together during shaking.
Yes. Unreinforced masonry is notoriously dangerous in earthquakes because the bricks just shake apart.
Right.
Incremental rehabilitation allows a hospital to vastly improve its safety profile over, say, 5 or 10 years without ever stopping patient care.
And for a hospital, surviving the initial shaking or the storm surge is only step one. It has to keep functioning. The sources introduce a concept gaining a lot of traction right now called passive survivability.
Passive survivability is designing critical buildings to maintain livable temperatures and baseline conditions even when the entire power grid fails.
So what does that actually look like in practice? Does that involve thermal mass?
Yes, thermal mass is a huge component. Thermal mass refers to materials like thick concrete or stone walls that absorb heat during the heat of the day and release it slowly at night.
Oh, I see.
If a hospital loses power and the backup generators flood, passive survivability means the building was designed with enough thermal mass, natural ventilation, and daylighting that patients won't freeze in the winter or suffer heat stroke in the summer.
The architecture itself protects them passively.
Exactly.
That level of foresight is vital. And speaking of foresight, we have to look at our transportation lifelines, specifically the bridges. I found a paper by researcher Takato Yasuno published recently in January 2026.
Yes.
Yasuno presents a technological advancement for bridge maintenance, an AI-assisted multi-stage inspection system.
This represents a vital update to our traditional engineering methods. We have thousands of aging bridges, and sending human inspectors to hang off the side of every single concrete pier is slow, expensive, and, frankly, dangerous.
Yasuno's system uses computer vision to autonomously detect vulnerabilities. But what makes it so effective is how it differentiates damage. Like, how does a computer vision algorithm distinguish between a harmless surface scratch on a concrete pillar and a lethal microcrack that compromises the rebar?
So the AI processes high-resolution imagery using pixel-level contrast analysis. A surface scratch typically has uniform depth and shadow.
Okay.
But a structural microcrack, especially one indicating internal stress or expanding corrosion on the rebar, displays specific geometric patterns and variable shadowing.
Oh, interesting.
The system is trained on thousands of images of structural failures, allowing it to flag deep vulnerabilities long before human eyes would ever spot them.
And it integrates location anonymization to protect privacy, ensuring that public infrastructure vulnerability data isn't exposed to bad actors, while still allowing agencies to prioritize emergency repairs.
And this raises an important question, because using AI to find cracks in concrete is a major leap forward, but it raises a deeply complex issue regarding how we maintain older infrastructure. The climate itself is changing the baselines.
You were talking about the fact that the 100-year flood isn't really a 100-year event anymore, right? Our historical data is suddenly obsolete.
Yes, exactly. Take a look at the Federal Highway Administration data on a phenomenon called scour.
Scout.
Scour happens when fast-moving river water hits a bridge pier, plunges downward, and creates a horseshoe vortex.
Okay.
This fluid dynamic vortex erodes the soil and sediment right out from under the bridge foundation.
It essentially scoops the earth away from the footings.
It does. And our older bridges were engineered for the river volumes and currents of the 20th century. But with heavier, climate-driven rainfall, river currents are carrying more volume at higher velocities.
So the scour effect is accelerating.
Exactly. A bridge might be perfectly structurally sound above the water. The AI might not find a single crack. But the climate-altered river is secretly digging a void underneath its foundation.
So what does this all mean for us? We have covered a vast amount of ground today, and what we've seen is that true resilience is not just one magic technology. It is a tapestry of carefully chosen engineering decisions.
Absolutely.
It's the mathematical formulas of the ASCE 7 codes. It is the continuous load path holding your roof down against internal pressurization. It is the 5-foot non-combustible zone and the baffled venks starving a wildfire of embers.
Right.
It's wet floodproofing, breakaway walls, and proactive AI-assisted inspections keeping our lifelines functioning.
Disasters are inevitable. The forces of nature will always test our structures. But disaster damage and the resulting tragedies are largely preventable.
And that is where I want to challenge you, the listener. Take a look at your own surroundings today. Walk outside your house. Do you have a clear 5-foot zone around your foundation? Or is there dry brush leaning against your siding? Do your attic vents have mesh to block embers?
It's worth checking.
If you live in an earthquake zone, have your local schools or your apartment building been evaluated for a soft story retrofit? The illusion of permanence is strong, but once you start looking for the engineering, you see the vulnerabilities and the solutions everywhere.
I want to leave you with one final philosophical engineering puzzle. For over a century, our building codes and gold standards have relied on historical data. Engineers look backward at past weather, past floods, and past wind speeds to predict future risks.
Right.
But in an era of rapidly changing climate extremes, the baselines are shifting. How must the engineering world adapt its mathematical DNA when looking backward is no longer a reliable way to survive moving forward?
That is the ultimate question for the next generation of builders and urban planners. We started by talking about that illusion of permanence when you walk past a brick building. Hopefully the next time you see one, you won't just see a static object. You will see a dynamic machine fighting forces of nature designed with a hidden logic meant to keep you safe. Thank you for joining us on this deep dive. Stay curious, and we'll see you next time.